Good afternoon. My name's Nigel Turvey. I'm the Network Strategy and Innovation Manager at Western Power Distribution. Welcome to our webinar describing some of the work and some of the implications of the work we've done looking at strategic investment requirements in the southwest on the network. As I go through the presentation this afternoon, if you would just post any questions you have, and I will address those at the end. If there are any I either don't manage to get to or I need to get further information before being able to answer them, we will respond to you via email. So I expect to take just over half an hour to go through the presentation. So the objective of the work we've done was basically to forecast the growth in demand and generation over 4 economic scenarios, to assess what happens in terms of thermal and voltage constraints across the network under these scenarios, which would limit the ability for connections to take place. Was to assess the high-level options for reinforcement, and via that provide stakeholders with advance notice of either likely constraints or the types of reinforcement that may come up. And it was also there to try and provide any recommendations for low regret investment, in other words, things which are under multiple scenarios but probably necessary, and so therefore things that we need to start thinking about getting on with. By way of background, I mean, the network was designed for demand. The current maximum demand in the southwest is around 2.5 gigawatts, with a summer minimum demand of just under 1 gigawatt. We've seen significant growth of distributed generation in the southwest. Brief summary there on the table highlighting we've got over 1 gigawatt of connected solar PV in the southwest. And the particular significance of solar is that that gives its maximum output around the time of minimum demand, not quite at the time of minimum demand, but around the time of minimum demand. So therefore, you know, we're already at a position of certain parts of the network will see exports under those conditions. Solar isn't the only generation there. We have a fairly significant amount of onshore wind, and we also have an increasing amount of other technologies out there. In terms of how we've got to today in terms of being able to connect to that amount of capacity, we've had significant usage of the inherent capacity, and that's been used up by both the connected and is also allocated to contracted generation. We're seeing both the cost of getting connections and the timescales of associated reinforcement, obviously delaying people being able to be connected, and hence people are more attracted to alternative connection arrangements, which usually involve constraints, or they start to look elsewhere on either our network or other networks in the UK for their allocation of their generation. Although it has to be said, many networks across the UK are increasingly facing similar issues. We have a major route into the southwest called the F route, and we did have an issue where we had to limit the connection offers due to a constraint on that route. Whilst that has now been lifted, clearly that caused uncertainty during that process. We also have a process of dealing with National Grid in terms of the impact of things connecting to our network on the whole transmission network. That's dealt with under a statement of works process. That also has introduced delays into what's happened and uncertainty, and all those uncertainties together have caused generation customers difficulties in being able to commit to their projects, and that's partly the reason for doing this work, to try and understand better what the issues are going forward on the network. We have seen a reduction in volume of applications for large-scale connections. This is obviously mainly driven by change in subsidy arrangements, but we're still seeing reasonably significant amounts of offers on the network needing to be sent out, And we're still seeing the cost of the technology going down, and excluding significant grid reinforcement costs, price parity for some of these larger projects, particularly solar ones, could be reached fairly soon. So therefore we may well see a subsequent increase in the volumes of people seeking to connect to the network. Just another piece of background, I think it's worth mentioning the Committee on Climate Change report, which came out in June this year. Whilst that was actually published after the work we did on this study was complete, there are a couple of key messages I've sort of pulled out there, which are really indicating that there is still a significant need for further renewables being connected to the network if the UK is to meet its climate change targets. And the committee there is highlighting that there are some administrative issues that really regulator and government need to deal with to be able to produce more certainty with projects being able to progress. The work we've done, as I say, is underpinned by some scenarios of the volume of generation and the changes in demand that we might expect to see over the next 15 years. In order to pull those scenarios together, we've used Regen Southwest, who have helped by doing those forecasts for us, particularly focusing on the DG, but also producing the heat pump and electric vehicle forecasts. These have been done over 4 economic scenarios. These are the same economic scenarios as National Grid use in producing their future energy scenarios for the GB. So we have the 4 scenarios of gone green, consumer power, slow progression and no progression. On the slide there it gives a sort of very high level summary of what's behind those scenarios. And as you can see by the sort of blue bars up the outside, they're trying to cover the range of sort of green ambition and prosperity that the UK might see in terms of where those scenarios might fall. What Regen have done is use those background economic scenarios to look at the growth in DG or heat pumps, electric vehicles that we would see in the southwest, taking account of the resource, demographics, etc. in the southwest. But they've also forecast at a fairly disaggregated level so that we know whereabouts in the southwest we might see these things happen, so that we can actually look at the impact on the network. Just going a little further in terms of the methodology they've used to produce these scenarios. What they've actually done is, as a stage 1, they've focused on ensuring we understand what's already connected to sort of validate the databases that we have. So we actually set a proper baseline, and that's had to be split down into obviously technology types and locations, and within that process they've picked up historic growth trends. Second part of what they did was to look at the near term. So this was very much focusing on projects which were known about, which have potentially grid connections, which are in the planning system, and they obviously talked to a number of these developers to actually understand the expected progress on these projects. So we were trying to get as close as we could to what could be reasonably expected in that near term. Obviously took in constraints like the issue of grid. If someone doesn't have a grid connection at the present time, that may be difficult to actually get short term, and policy changes in terms of where things are going on subsidies. They then look to the longer term growth in terms of factors such as the developable resource, demographics, planning systems, long-term energy assessment. So actually fit that against the 4 scenarios we have to give an output. As an example, here's the onshore wind output for the southwest, showing those 3 stages of the current baseline, the pipeline projection, and then the growth scenarios going out into the future. In terms of the output from these scenarios, this slide and the next one sort of just show the total amount of distributed generation we might see connected to the network. under those 4 scenarios. So as you can see, it's covering quite an envelope of potential outcomes. It's the same data, but obviously presented slightly graphically differently. One of the features you can actually see with this graph in particular is the sort of relatively flat period that we're entering now, and that really is the impact of the expected change in what's happening on subsidies, the issues that are out there in terms of some of the grid capacity issues, and hence sort of flattening off in the amount of connections. Then obviously as we potentially start hitting price parity on some of the technologies, we will see potentially some quite rapid growth again. We took those, the output of that scenarios, and we're then wanting to see what impact that actually has on our network. We focused on the subtransmission network, and by that I mean the interface, the grid supply points between us and National Grid, our 132 kV network on the predominantly steel tower side, and the transformation from that network down to our lower voltage networks. The reason we focused on those is because these are the areas where gaining consents can be most protracted, and also the actual construction times can be longer. So therefore, the more notice you have of these issues in these areas, the better. One thing that was different about this modelling to what's been done previously is, previously we focused very much on peak half-hour, minimum half-hour type demand conditions. We recognise that load shapes are changing and generation output profiles are changing as we get a different mix of generation. So therefore we decided to model each half hour of 3 representative days to actually see where the worst conditions are, because it can be a combination of different demand and generation outputs which can cause us issues. So we've done that for 3 representative days, and we've also looked at all the credible first outage, so first faults on the network, and then also second circuit outage conditions, which essentially is looking at where you've got a maintenance outage on the network and then you have a fault that follows it. The profiles of generation and demand that we used were determined using a combination of historic data that we have and obviously modified for the growth in the technology types we were seeing, or for demand in terms of the electric vehicle take-up, etc. The analysis we've undertaken was done for the baseline year, make sure we're getting output that looks realistic in terms of what we actually see on the network, and then scenarios we looked at for 2020 and 2025. Going beyond 2025 is quite tricky at this stage, and there's 2 reasons for that. One is, and I'll come back to this in a minute, but one is we're waiting for some analysis that National Grid are doing in terms of the impact of these scenarios on their network. So therefore, if there are changes to their network, it can affect how our network will look. And also, certainly at the time we were doing the study, significant uncertainty around Hinkley Point C being connected to the network. There's clearly still some uncertainty around that in terms of the exact timing, and potentially some uncertainty over a project when it actually gets built. But I think there's more certainty now that something will happen in that area. In terms of the results of that network modelling, clearly whilst it wasn't an objective of the study, it did allow us to confirm the validity of some of the reinforcements currently underway. In particular, the F route, the split of the 132 kV circuits towards the north of our patch. Some work down at Fradden, which is central Cornwall, the addition of further transformer capacity and circuit upgrades in that area, and also the enhancement of a 132 kV route in North Devon called the J route. Looking out towards 2020, we certainly identified some further reinforcement issues, or issues that we need to look at, which fall really in that pipeline territory of what we can expect to be connected to the network. One of those at the top there, K route. This is a route which runs from North Devon down into Cornwall, a 132 kV route, down that west coast of the southwest, and that will need work doing to upgrade it. And we also may need to look at the interface capacity between us and National Grid in terms of the transformer capacity at those grid supply points. Also down, in effect, the other side of the southwest, between Abham, Exeter and Landulph grid supply points, and this essentially geographically is between sort of Exeter, Torbay down towards Plymouth. Again, we have networks that run in parallel with National Grid, and we are seeing issues on those interconnectors that we will need to address. We also have a 132 kV circuit near Exeter, and then we have some other issues there highlighted. There's some transformation groups just to the west of Plymouth, Landulph, St Germans, and then there's the associated 132 kV circuit which runs from St Germans across to Indian Queens down in Cornwall. The Pyworthy North Taunton group is actually one which sits partway down K route at the top, the first issue I mentioned. So again, we have some transformation to lower voltage capacity issues there, which we may need to address with circuits as well as transformer capacity. I mentioned active network management becoming more common in terms of the offer that's made to people. And active network management essentially just constrains generation off at times when we're unable to export all of the all the generation which is being output. Sorry, I think there was an interruption on the audio there. I'll carry on though now. Active network management isn't the solution in all circumstances. Some of the limitations, obviously there's a commercial limitation in terms of the degree of acceptable curtailment of generation output. As we head towards higher amounts of time that we curtail generation for, that clearly impacts the income of the generator and hence is unlikely to be economically acceptable to the generator. But in addition to that general commercial limit, there are some technical limits we have to be careful of in the application of active network management. First one, their complexity. Clearly, we've got some fairly interconnected and complex networks out there. And when we have multiple issues on those to address via an active network management system, this can lead to overlapping constraints, which can lead to very high levels of forecast constraint. And when we get those, that can really destroy projects in terms of commercially, because economically they couldn't suffer that level of constraint. We also have to be slightly careful about equipment ratings. Our equipment is rated in terms of the amount of current it can carry, really based on the assumption that we are going to see a cycling of load. It will go up and down during the day. However, if we have extensive use of active network management, we are beginning to flatten that load curve, so we're beginning to fill in some of those troughs. And hence we do have to be careful about the ratings that we use on the assets under those circumstances. And then finally, we also have equipment out there which protects the network when we have a network fault. So it's detecting, very high currents when it's connected to earth by something touching a line or an underground cable faulting. That operates in very quick timescales. Active network management operates in probably tens of seconds or minutes in terms of its operation. So clearly, if we're trying to reconfigure a network where we actually have very short-term high overloads, there's a risk the protection will operate before the active network management. So we have to be careful about the design to make sure we don't go into that territory. It is possible to operate in that area by pre-curtailing generation under certain operating or load conditions. But again, if you do pre-curtailment, that then increases the amount of constraint time and puts the economics of projects at risk. I've mentioned the national transmission network a few times and the interface with National Grid. So between us, we have commercial arrangements, and as part of that, we tell National Grid when generation connects to our network, gives them the opportunity to assess whether that has any impact on their network, and that's done via a process called Statement of Works. And where things are identified, there's a modification application process that follows on from that. And what's really come out of that process is that we've either reached or are reaching the limit of the transmission system in the southwest and are having to increase things like active network management to accommodate further generation. To understand the transmission issues that arise under these scenarios we're looking out to 2030, we've done work in terms of improving the exchange of network data between us and National Grid. We are actually trialling a revised version of the Statement of Works process to try and speed up the information we can give to customers and try to give more certainty. And we've also agreed with National Grid that they will undertake some detailed studies against our scenarios on the impact on the transmission network and assess whether there's any work that they need to do. In addition to that, running in parallel, there's some detailed discussions going on with National Grid on the future planning and operation of the combined transmission distribution networks. So this is really making sure we look at a whole system analysis to make sure that if we need to undertake investment or further control action within the network, that it's done at the right level and on the right network. The recommendations from the report are obviously really to address those issues I highlighted earlier, which came out of it. The first one being the K route over down the west coast, and the grid supply point capacities at Indian Queens and Albadiscot. It's one of those where we also do need to consider whether an additional grid supply point is going to be required in that area to actually relieve some of the conditions we would see under some of the higher growth scenarios of DG. There's also detailed consideration of those other areas that I looked at. Whilst we've looked at some high-level potential solutions, clearly we need to do a proper economic analysis for those to make sure they are the right ones if we're going to move those forward. We also will need to revisit this to some extent once we have that analysis by National Grid done, because if they are going to change any configuration on their network or capacities on their network, then clearly that will affect the flows and conditions on our network. So therefore we will need to adjust and check that things are still valid that we've come out with so far. As I indicated, we will need to continue with our analysis on ensuring we really understand the technical limits of active network management and make sure we don't breach those as we move forward. What's also been highlighted in the study is a number of areas where we run up against issues on the parallel running of our network with National Grids. Now, whilst that's served us extraordinarily well over the years in terms of when we've had a network which has been purely demand, we are now finding that with the increase in distributed generation and sources of generation on our network, that does appear to be causing us more problems on those interconnectors and the parallels. And hence we do need to understand strategically whether we need to start moving away from that interconnection and start breaking some of these groups up. And then finally, we're seeing this as part of a continuous process. We are started in the southwest. We've already started to do similar studies in South Wales. We'll move on to our Midlands networks after that, and hence we're looking at a repeat version of redoing the southwest in a couple of years' time to pick up changes that have happened in that time period. One obvious question which comes out of all this is how is upgrades or reinforcements that are deemed necessary paid for. Well, we will continue to apply the current charging methodology approved by Ofgem, which is where a connection triggers reinforcement on the network, so those ones that we've indicated earlier in this. Contribution towards the cost of those reinforcements will form part of the connection charge. However, it is becoming more difficult in some circumstances to clearly determine the cause of reaching the limit on the network. And this is caused partly by, there is a slow but steady reduction in demand levels. Really, that's a combination of efficiency at the end use and also the increase in behind-the-meter generation, so small-scale PV and such like being installed on rooftops, which are effectively shown as a lower demand level on the network. Another issue is we're also continuing to see connections at high and low voltage, smaller projects. Under our connection charge rules, these don't contribute to the cost of 132 kV reinforcement works. Now, whilst it is possible for us to say you must wait till we finish those reinforcement works, that is all done on the assumption that we're going to see the sort of larger EHV connections proceed. Some of these don't over time, and so therefore getting that confidence of the timing of when we need to do reinforcement can be quite difficult. So therefore we are seeing that steady increase in HV and LV connections, which slowly eats into any capacity we have and can then cause us to have to trigger reinforcement. Then finally, we are obliged to give an offer up to the limit of the network. So therefore, once an offer's been made and that generation is going ahead, if we then see a reduction in demand levels, that will trigger reinforcement. And you can't really attribute it to a generation retrospectively. So where we are is we have actually reached the point where certain reinforcements, and I think I've referred to some of these, the F route, Fradden, and that K route down the west coast, are being classed as general reinforcement due to not being able to attribute those conditions to specific connections. During the study, we've also sort of come across other issues that we need to think about as a company. One is abnormal operating conditions. So these are when the network is running, either it has a system fault on it, so it's running abnormally, or we've had to take an outage on the network to do maintenance or to connect another customer. Whilst the connection agreements with generators give us the right to constrain generation under these abnormal conditions, clearly the generator would like us to be able to forecast that upfront before they're connected. That we find very difficult to do with any degree of certainty. We give estimates to our best of our ability, but clearly things like when people are going to connect to the network, we don't know at the present time. So therefore it can be quite difficult to give reasonable forecasts going out to the future. So going forward, a method process is needed to really demonstrate when that risk is getting too high for generation and when it is economic to undertake reinforcement. In other words, where is it appropriate to impose constraints on a generator, and where is it more appropriate to undertake investment on the network and reinforce it so those constraints aren't needed. I believe the best way to start addressing this is to start better defining the commercial rights that generators have. And once you define the rights, you can then actually define the conditions when compensation might be payable, or when you at least accrue an economic case to undertake reinforcement. So therefore that would start giving us that good signal as to when reinforcement is more appropriate than further constraints. Further issue which is out there at the present time is what's known as the P2 review. P2 is the security standard that we actually design networks to at the present time. It's defined in our license. And one of the things which is coming out of a review that's going on about that standard at the present time is that there is no economic case for the security supply for generation, essentially any generation connected to distribution networks. Whilst the economic case appears fairly clear in terms of, the maths and when you calculate it out. There is a question certainly in my mind in terms of, is this the right long-term policy given the continual growth in distributed generation and the increasing importance that that's going to give to overall security of supply for the UK. At the present time, National Grid, I think, are in their second cycle of producing what they call their system operability framework. That mainly covers issues associated with the transmission network at the present time. And hence, we've also looked at some of the operability issues associated with the distribution network. And hence, some of the issues that we've come across while undertaking this study, we're looking to incorporate into a distribution version of a system operability framework that we're currently working on. Now Grid, I think, have recognised, as well as everyone else, that there's a lot of whole system issues out there, and hence we do expect the National Grid system operability framework will evolve into a whole system version over time. Just to highlight some of the things that we have come across, although it is in a very early stages of development at the present time, this distribution system operating framework, here's a few of the subjects that we've been looking at. I'll just say a few words about at least some of them. Top one there is arc suppression coils, or Peterson coils. This is a particular form of earthing system which is used particularly where you have ground conditions which make earthing more difficult, but also has the advantage that it can actually hold single-phase faults on the network for a period of time before you actually interrupt supplies. One of the things we have found in Cornwall, though, is it's very dependent on the impedance of the network. That changes as you change the equipment connected to the network. And as we've connected more and more cable to the network in Cornwall, we are now seeing increasing issues with that form of earthing. And hence there will come a point where we will need to switch that system over to a more conventional form of earthing used elsewhere. Clearly, we need to understand the right economic point at which we should do that. And that would obviously form part of this ability framework. Fault levels, the changes in the nature of generation in terms of its type, and also in terms of the mix between what's on distribution networks and what's on transmission networks, will have an impact on fault levels. That impacts on things like power quality, in other words, whether you see dips and harmonics on the network, but also could potentially affect our protection systems. So therefore, we need to understand how that will change in the future. Vector shift protection is a particular form of loss of mains protection. We put loss of mains protection on generation connected to the network to ensure that we end up with a safe and secure network should things happen and go wrong. There is some concern over the stability of that, and we do need to look at those issues in terms of long term, whether that continues to be the right solution, whether there are other things we need to do to it. Active network management, I've talked about this already, but clearly there are limitations, and clearly we need to make sure it's properly interfaced with National Grid so that we have whole system control when we're doing active management of our network. Voltage control, again, we now have multiple sources of potential voltage on the network, which we didn't historically have, and hence we do need to make sure we're assessing how we control voltage across the network, whether the equipment we currently have is the right thing, and whether things work as they should. So that's another area we need to look at. Dispatch and outage coordination, this is really about the abnormal operating conditions, and we're certainly already undertaking work with some of the DG developers to try and make sure we improve the communication in terms of constraints which are coming up and what we may be able to do to help reduce those constraints. Next one, low frequency demand disconnection. Again, this is a sort of national system which is there to defend against very sudden changes in demand or generation due to major faults on the generally on the transmission network, and is there to ensure the system remains stable and that we don't have a larger loss of supply as a result of those events. There's a risk that that can be degraded and operate less effectively as you add more generation to distribution networks, and hence, again, assessment is needed to make sure that will continue to operate effectively, or if not, to have time to plan to change to other systems to deal with that issue. Then finally on that list, network monitoring and modelling. We are going to need more modelling as the network becomes more active. We need to understand what's happening. We're going to have to move that modelling closer to real time, and we're going to have to probably have a lot more monitoring out there so we really understand what's happening as the network conditions change. So, in summary, this is the first time we've undertaken such a long-term comprehensive analysis of the network. It's certainly the first time we've done sort of a half-hour by half-hour analysis over a day. During the modelling, we've looked at a significant envelope of potential changes in generation and demand to try and make sure we capture the potential issues we're going to see going forwards. We've got further work ongoing with National Grid to make sure we do look at the whole system issues which are out there and can look right across the southwest in terms of what the potential impact over time is. We have highlighted other issues that we really need to consider under a probability framework, be that either a distribution one on its own or over time to incorporate some of those into a national system or probability framework. We obviously learned lots of lessons as we went through doing this study, being as it was the first time we tried to do it this way, and we are building the lessons that we've learned during that process into the study we are starting on South Wales network. And then finally, this is the start of a long-term cycle of assessment, so that we try and keep this longer-term view as to how the network needs to develop over time, looking outwards in terms of the likely take-up and changes of the use of the network. So finally, we're putting all the reports and this presentation will be available from our website. The address is up there on the screen. And if you have any questions or inquiries about what we're up to, there's an email address there, and we'll get back to you as soon as we can. So, thank you for listening. I'll stay on the line just for a few minutes to see if there's any questions. Right, I have one question come up so far in terms of the F-route constraint, in terms of remaining until October 2017. In terms of where we are on F-route, the offers going out at the present time are not constraining generation. Essentially, we are relying on the issue that there are a number of connections out there, and when we look at the timescales of when they're going to connect, we are expecting sort of the staggering of the actual connections to be such that we are able to allow connections to proceed in the interim. So hopefully that answers that one. In terms of next question I have here is about the change in demand due to energy efficiency, and asking about the impact of electric vehicles. And yes, we did, as part of the scenario development, we did look at the growth in electric vehicles and electric vehicle charging, and hence how that would change demand. And that has been factored into the scenarios that we use to actually develop the study. Next one is about Hinkley Point. How do we see that affecting connected customers? In terms of connected, I would hope it would have a relatively low level. I mean, clearly there will be construction outages associated with the Hinkley Point works, which have the potential to affect some connections in terms of constraining them during some of that construction work. But I don't think that is significant, because I don't think there is any generators actually connected to assets which will be completely removed as part of the Hinkley Point works. Projection for the roll. Next question is about the projection for the rollout of grid level storage capacity within WPD's area. Storage is probably the area we've struggled with most in terms of forecasting. Whilst we've got some very high level estimates of the sort of volumes of storage, and they potentially could grow quite quickly, actually modelling the profile that we would see on that storage is actually quite difficult, because until we see more development of some of the economic models, we really don't know at what time they will be importing energy to charge up and exactly which times they will export energy. So therefore we haven't taken a huge account of those in these studies at the present time. What we are looking to do is commission some work to better understand the profiles we will see on storage going forwards, and hope to incorporate those as we get those issues. Another one was, is there a start date for the cave route reinforcement? I don't think I've got an actual date at the moment. We are certainly progressing the studies and works to actually get that going, though. We are seeing that as a relatively urgent thing to move forward on, to at least partly lift the capacity. It may be a multi-stage reinforcement that we undertake on that network. Further one on storage. In terms of, is it a potential solution? It certainly is a potential solution to part of the issues. Storage is very good at being able to take off the very short-term peaks on the network. Clearly, if it's not a short-term peak, storage gets more difficult, because although storage is very effective at removing short-term peaks, the total volume of energy, the quantity of energy you can get into a storage unit isn't that great compared to the output of some of the DG we see. So therefore it's can be very useful to just peak shave, but certainly isn't capable of sort of bulk shifting of output. Further questions on storage, and certainly on things like demand side response. I mean, part of what we're hoping to do with some of this output is where we start, as we start understanding the reinforcements that are needed, we can actually see the costs of those and hence the impact of those. So therefore they will give us a better handle on the value to us of storage and demand side response. Now clearly that is part of the picture for providers of those services, because if we can start indicating to people the value that it is to the distribution network of that storage or demand side response, that can then they can then stack that with income they can get from other sources, so where National Grid is looking for services and where suppliers are looking for services, onto their business case, so they can understand the true economics of how things work. The expectation is that most storage systems will not be economic just addressing one service. They're going to have to be able to enter a number of markets to actually make the project, truly economically viable. So therefore, part of the purpose of the study we're doing is we can start to get some of those numbers out in terms of understanding the cost to us of the network, and hence if someone can provide that service, the impact on the profile by using storage or demand-side response at a lower cost, then clearly that's the right thing to do. There's a further one in there that I probably missed earlier about electric vehicles and essentially whether there's the opportunity for vehicle to grid, in other words, using the batteries in vehicles to provide as a storage for the network, in other words, not just used for the vehicle. Yep, that is definitely a potential service for the future. We do have some projects which are starting to look at that issue in terms of vehicle to grid and trying to understand, the issues and ensure that, which needs to be a joint project with some of, say, the vehicle manufacturers, etc., because we do need to understand whether there are any issues with the cycling of the battery in terms of whether we have any effect on its life or its performance as a result of doing that, of using cycles for the network. But it's clearly a potential large source of storage which is being already invested in for other purposes. So it's one we must look at and must find whether there's a viable service package within that. The questions appear to have dried up for the moment. I'll just wait another minute or two. Oh, there's one more. Hold it. Okay, it doesn't look like there's any more questions coming through. Oh, there's a further one about whether distribution network operators should become system operators. In many ways, the distribution companies are already becoming system operators. I mean, that's really started with the use of active network management. So we're already changing the way the network operates as a result of that. So, I mean, that's the start of the process. It's a very, slow start to some extent in terms of the full system operator role. I think one of the things we do need to get to agreement on is exactly where that boundary is between what distributors do in terms of system operation and what is continued to be done by the overall system operator. So, for example, at one extreme, you've got frequencies. Sorry about that. I just saw the sound had disappeared again. I think I got up to a for example before the sound had cut out. For example, in frequency control, there's a decision to be made there whether that continues to be a responsibility of the overall system operator or whether you somehow devolve that right the way down to distribution networks to actually balance demand and supply. Yeah, that's clearly an extreme case as to where you could go in terms of the split of system operation. But we do need to start building the case as to where that boundary is. But I do see a further evolution of the the distribution system operators, certainly in achieving balance in dealing with constraints on the network and of assisting with constraints on the national transmission network in terms of achieving that balance. Whether that goes all the way through to achieving an energy balance on distribution networks, I'm not quite so sure about at the present time, but certainly there's a lot further to go. And then there's a final one in terms of what might be needed in terms of system sensor enhancement. I mean, one of the things I did highlight there is we do need to look very closely at the modeling capability that we have on the network. And as that needs to get closer to real time, as we move more closer to being a system operator, we are going to need more sensors on the network to actually make sure we really understand what's going on out there. So modeling does part of it, but you do need some sensors to make sure the modeling is accurately reflecting what's happening in the real world. So there is further investment to be made in those areas. Okay, looks like there's nothing else coming through at the present time. As I said, there's the email address to come through with any further queries. I just want to thank you all for joining our webinar and listening this afternoon. Thank you very much.